Good afternoon, everyone. The topic of my presentation is practical physical attacks against embedded systems and their secure design to mitigate them. My name is Rohini and I'm currently working for Bosch PSIRT that is located in Stuttgart, Germany. This is the agenda of my talk. I would start with an introduction to physical attacks, then briefly mention different types of physical attacks, that being supply chain, side channel invasive imaging and test-based attacks. Then I would like to give some practical examples on some of these attacks and finally talk about safeguards or secure design to mitigate them, followed by conclusion. Because of the time limitation, I might not go into the depth of each topic. Nevertheless, you could have a look at the notes or the research papers I have referenced. As a part of my day-to-day job at PSIRT, I come across several vulnerabilities that are not only in software but also hardware. Such vulnerabilities require local or physical access to device to be exploited, and such attacks are known as physical attacks. So these attacks or vulnerabilities cannot be patched via software means, and upgrading the hardware of the devices that are in production or already deployed is not only challenging but also very expensive. That is the reason why secure design of such devices are very critical, and it is also important to understand what are all the different types of attacks and motivation behind those attacks to come up with a secure design. The first type of physical attack that I want to talk about are supply chain attacks. Usage of system on chips have increased drastically over a period of 10 years. As a result, the SoC manufacturers, in order to reduce the time to market and prices, they start integrating third-party intellectual property with their own intellectual property, and they also started outsourcing the fabrication and packaging to a third-party entity. As a result, there could be a malicious third-party intellectual property vendor or a malicious fabrication house that could reverse engineer the intellectual property or the ICs, or clone the intellectual property, or even introduce hardware trojans. So hardware trojans are malicious modules that are inserted with an intention to maybe bypass security feature. So as an example, hardware trojan in a cryptographic module such as a random number generation module could always generate predictable outputs. Another type of physical attacks are side channel analysis attacks. These attacks are non-invasive attacks. In today's talk, I want to briefly mention about power analysis, electromagnetic analysis, and fault injection attacks. Power and electromagnetic analysis attacks deal with measurement and analysis of physical attributes of device during runtime. Power analysis attack deals with interpreting power consumption measurements collected during the cryptographic operation. This can be divided into simple differential and correlational power analysis. Simple power analysis, as the name suggests, deals with deriving of the key more or less directly from the power traces without applying any statistical means. Differential and correlational power analysis, on the other hand, they use some sort of statistical methods to derive the key. DPA is based on the principle that there is a significant power variation between manipulating zeros and ones. For known input and guessed keys, output of intermediate operation, say S box, is computed. Such computed values are used to divide the power samples into different categories, and then you perform correlation between those categories to derive the key. Correlational power analysis reveals the data leakage by finding the relationship between the characteristics of power traces and a hypothesized power model. Aim is to find the correlation between the predicted output and the actual power output of a device. So you could use either Hamming distance or Hamming weight power model. Electromagnetic analysis attack deals with capturing electromagnetic emanations from the device and using them to derive the key. Electromagnetic analysis attack is further divided into simple, differential, and correlational electromagnetic analysis. In fault injection or glitching attack, an attacker changes the current functioning of the device by creating variations in either voltage level or injecting irregularities in the clock signal or electromagnetic disturbances, overheating the device or exposing it to intense light and so on. So these two diagrams, they show clock glitching. So in ATmega 328P. So the first diagram shows a regular clock cycle, and in the second one you can see that there is a clock irregularity, and as a result the execution of the first instruction is skipped. So such attacks could be used to bypass security features such as secure boot. Another type of physical attacks are invasive attacks. They are called as invasive because the attacker is required to either mill down the silicon substrate using focus ion beam, for example, or remove the passivation layer using laser cutter in order to directly probe the internal wiring of the device. The motivation behind such attack would be to connect directly to the internal wiring, say data bus, address bus, read the data from the memory, or read the data that is flowing through data or address bus. Imaging attacks, they use some sort of light source such as laser beam to scan the device, and then the stimulation from the device could be current, could be the light reflected by the transistors, that is somehow measured and visualized in a way that could be used to reveal the key. As you can see here, using visual means you could reveal a secret from the device. In this particular example, it is a plain text bit stream that is stored inside the FPGA. Last but not the least, we have test-based attacks. Two types of test-based attacks are scan chain-based attacks and JTAG-based attacks. So scan chain are designed for testing methodology which uses scannable cells connected to form one or more scan chains, mainly used to make sure that the chips are not faulty. Such scan chains could be used to extract secret keys from the device. And then you have JTAG based attacks. So if the JTAGs are left open in the devices, it could be used to dump the memory contents and reveal the key, or reverse engineer intellectual properties, or bypass security features, escalation of privilege, and so on. So the first practical attack that I want to talk about are supply chain attack. So in this particular example, the researchers introduced a hardware Trojan in the FPGA and used accelerator coherency port to access the application processor unit's memory. And with such an access, and with changing or setting certain bits to 0, they were able to gain access to the secure world memory. With this, they were able to update the OPT binary that was stored in the DDR memory with an intention to change it in such a way that the signature verification of the trustlet is completely bypassed. And finally, they were able to run an unverified trustlet in the secure world. This practical fault injection attack involves bypassing secure boot in ESP32. ESP32 is a low-cost system on chip extensively used in IoT devices. The bootloader image, along with the public key, which is used for verifying the signature of the application image, is stored in the SPI flash along with the digest that is computed in this way using the secure boot key. Now, when the device is powered on, the boot ROM will recompute the digest and compare it with the digest that is already stored in the SPI flash. If there is a mismatch, then error message is printed on the UART. So by reverse engineering the boot ROM, the researchers found that just after the last SPI data frame is seen and just before the error message is printed on UART, that is exactly the right time where voltage glitching needs to be applied. And with this voltage glitching, the researchers were able to bypass the secure boot. A practical example of imaging attack is a thermal laser stimulation attack. The researchers used this attack to reveal the key from the battery backed up RAM of a Xilinx ultrascale board. They used laser scanner to scan the board. This caused the transistors to heat up and generate current on the VBAT line, and this stimulation was then passed as an input to image acquisition tool to visualize the results. So using such means, they were first able to localize where exactly the BBRAM is located, and within BBRAM they were able to also localize where exactly the keys are located, and by visual means they were able to tell whether the bit is 0 or 1. The last practical attack I want to mention about is known as mode switching scan chain based attack. So the researchers based this attack on the fact that the intermediate result obtained after the first AES operation can be analyzed to deduce secret key for a 128-bit key length. In a crypto module, the encryption results that are generated after each round is usually stored in a state register which is part of the scan chain. So the researchers first applied a crafted plain text and ran the AES algorithm in the normal mode for the first round, and immediately after that switched to the test mode to get the intermediate result out of the device. So this process they repeated using pairs of plain text whose Hamming distance is 1, and on an average they require 256 pairs of plain text to crack a cipher key with a length of 128 bits. This is the final part of my talk. What are all the safeguards against supply chain attack? So there are two ways to either detect or prevent hardware Trojan. You could use something like called as code coverage analysis, which is the percentage of lines of code that has been executed during the functional verification of the design. This would give you a quantitative measure of the completeness of the functional simulation of the design. If there are some lines of code that have not been executed, then you could conclude that this could be malicious. Or you could use something like formal verification, where the SoC manufacturer would then give a set of security properties along with functional properties to the IP vendor. IP vendor will then have to prove that all these properties have been satisfied, and if there is a violation, then that could indicate the presence of a Trojan. And safeguards to prevent against Trojan insertion are very similar to prevention of reverse engineering or IP piracy. You could use some sort of obfuscation or camouflaging technique. For example, a layout level obfuscation to create indistinguishable layouts for different gates by adding dummy contacts, faking connection between the layers within a camouflaged logic gate. Or you could use something called as IC hardware metering. These are the techniques that are used for post-fabrication tracking of the chips. So there are two ways to do IC hardware metering, either passive metering or active metering. Passive metering deals with just tracking of the ICs post fabrication. You could use some sort of serial numbers on the chip or store a unique identifier in the memory to track the ICs, or you could use physically unclonable function based ID. And in case of active metering, these are all the mechanisms that are used to monitor, control, lock and unlock ICs post fabrication. So for locking and unlocking, you could use a public key infrastructure, or you could come up with a design of the finite state machine in such a way that only the correct input would unlock the feature.
The safeguards against power analysis attacks are: you could bury the power consumption in different kinds of noises. The idea being making it harder for the attacker to extract useful information from the power traces. You could also build a device in such a way that it consumes same amount of energy, or the power consumption of device is more or less random. You could also randomize or mask the intermediate values, because the results of the intermediate operations such as SBox are used to find the correlation between the predicted and the actual keys. Or you could use a key rolling technique, which uses different keys for encrypting different parts of the plain text. In order to prevent electromagnetic attacks, you could use an active shield to prevent the leakage of electromagnetic emanations, or you could introduce a noise generating non-functional module to make it harder for the attacker to derive the key from the electromagnetic emanations. Safeguards against fault injection attacks are: you could detect fault injection with the help of sensors. Sensors could detect variations in voltage, frequency, light, and so on. You could use error detection codes to detect fault injection in software implementation of cryptographic algorithms, or you could use instruction duplication or even instruction triplication to detect and even correct errors, and parity checking to make sure that the stored values are not corrupted.
Safeguards against invasive or probing attacks are: you could use camouflaged gates, dummy contacts, or you relocate the sensitive wires to lower layers, making it harder for attacker to reach or probe those sensitive wires. You could use an active shield. In this approach, the shield which carries the signals is placed on the topmost layer to detect holes milled by the focused ion beam, or you could use analog shield mainly to monitor and detect parametric disturbances with those wires. Safeguards against thermal laser stimulation attack would be to obfuscate the memory structure, making it harder for the attacker to localize the keys inside the memory. In order to detect such attempts, you could use light sensors. You could use an opaque coating to obstruct the optical path between the transistor and the microscope, and you could generate noise on the voltage line to mask data dependent current leakage. Electro-optical probing, on the other hand, uses incoherent light sources. So as a result, you could use ring oscillator based physically unclonable functions. So ring oscillators could be used to detect optical probing attempts, and electro-optical probing attempt would affect the behavior of the physically unclonable function with a high probability. Finally, the safeguards against JTAG based attacks are to obviously disable JTAG permanently, or you could use password protection for JTAG, but a more effective way would be to use cryptography. That is, you would authenticate the device using some sort of challenge response mechanism, and then you encrypt the JTAG communication channel, and you also make sure that unauthentic JTAG messages are prevented using HMAC. Safeguards for scan based attacks would be to obfuscate the data that is traveling through the scan in, scan out. You could use some sort of encryption to encrypt the test data in the scan chain, or use some sort of intelligent test control system. That is, whenever the switch is switching from normal to test mode, you reset the system to make sure that all the data in the scan chain is cleared. Or when the chip enters the test mode, you try to isolate the key from the cryptographic module to prevent the leakage of the secret information. The safeguards that I mentioned in today's talk are not only applicable to the SoC manufacturers, but also to the IoT device manufacturers who could use these to make the right choice when choosing a hardware. So we can finally conclude that the physical attacks against embedded devices and their impacts are becoming increasingly more popular. As a result, the physical hardening is as important as network level hardening. So investing in secure design and implementation is very, very critical to avoid unpatchable vulnerabilities. And exploiting vulnerabilities through physical means, of course, adds to the complexity of the attack. But in today's talk, we just showed that nevertheless they are achievable. Thank you all for your attention. Good day.